My name is Benjamin, and I will be presenting the paper Value Partitioning, a lightweight approach to relational static analysis for JavaScript, which is joint work with my advisor Møller from Aarhus University. The setting for this talk is sound static analysis for JavaScript. JavaScript is a very challenging language for static analysis due to its dynamic nature. The slide shows an example of a method call where x evaluates to an object and m evaluates to a string that is the name of the method. I will now explain some of the challenges when analyzing this method call. JavaScript has a dynamic object structure, meaning that the properties of the object x can dynamically be added and deleted. Furthermore, JavaScript names can be dynamically computed, and JavaScript also supports dynamic dispatch. So if the static analysis can't precisely infer both the object structure of x and the precise string value of m, then critical precision loss can happen in this dynamic dispatch, since the static analysis might have mixed a lot of functions together, and then statically, all those functions can be called, resulting in a lot of spurious callages. These kinds of critical precision losses therefore often render static analysis for JavaScript useless due to too much spurious data flow. In this talk, we will present a technique that improves reasoning about the object structure and also tackle some other challenges in JavaScript analysis. Let's consider the JavaScript program on the right, which copies properties from the object x to the object y. The copy happens by first reading the p property of x, writing it to the variable t, and next write the value of t to the p property of y. I will now show how a typical static analysis will analyze the code when the property name p is imprecise. On the left, we see the analysis state at the program point indicated by the black arrow in the example program, so currently before the property read. At this point, the analysis state specifies that x is an object with a foo property that has the value f1 and a bar property with the value f2, where f1 and f2 are functions. The analysis do not know the value of p, meaning that it's imprecise, indicated by the question mark. The value of y is an object without any properties. When reading the p property of x, we have to read both the foo and the bar property, since p is unknown, meaning that the abstract value of t becomes both f1 and f2. Then we analyze the dynamic property write, which writes the value of t to all properties of y, since p is unknown, meaning that all properties now point to both f1 and f2. In other words, all the properties of x have been mixed together in all properties of y. This results in the read of y.foo to be both f1 and f2, and at this point the analysis will now analyze calls to both functions. In this example, this precision loss might not seem critical, but this pattern often occurs in real-world JavaScript code, and there it's hundreds of functions that are mixed together. So far, there exist two techniques attempting to solve this problem precisely when p is imprecise, and I will now present the two and explain the limitations. The first technique is state partitioning, which is a technique proposed by Correlated. We explain the technique using the same program and initial abstract state as before. At the dynamic property read, state partitioning partitions the abstract state to a new state for each of the properties of x and one for the properties not in x. This means that we get an abstract state where p is foo, one where p is bar, and one where p is unknown, but a property not in x, and thereby the analysis can make a precise read in each state. The write is then analyzed precisely in each state as well, and the states are merged together afterwards. The important thing to notice here is that state partitioning avoided mixing f1 and f2 together. However, it is expensive to partition the state into multiple states, and therefore state partitioning is only applied when the object copy pattern can be identified syntactically. Therefore, this technique does not work when the read happens in one function and the write in another, which does happen in real-world code. The second technique is demand-driven value refinement, which was presented by Stein et al. At Uppsala last year. Again, we have the same code and initial analysis state as before. Demand-driven value refinement just reads the property as a standard analysis, so t can be both f1 and f2. Instead, demand-driven value refinement tries to regain the relational information at the dynamic property write. It heuristically sees that we are about to write an imprecise value, the value f1 or f2, to an unknown property of y. At this point, the technique asks two queries. What is the value of p when t is f1, and what is the value of p when t is f2? A sound backwards goal-directed analysis then starts from the dynamic property right and tries to answer the queries. For this code, it provides the precise answers that p is the string foo when t is f1, and that the value of p is the string bar when t is f2. By using these answers, it suffices to write f1 to the foo property and f2 to the bar property. This technique thereby avoids mixing together the properties, and it also works across functions. The limitation about this technique, however, is that it requires a separate backwards analysis for the full JavaScript language, which significantly increases the amount of work needed to further improve the analysis and add support for new JavaScript features. I will now show some challenges on real-world JavaScript code. The code is an excerpt of the Lodash library, which is the most popular JavaScript library. I will not go into details about the code, but point out some challenges faced when analyzing it. I will later explain the challenges on small examples. First, there are interprocedural read-write pairs. The value of key in line 14 is the same as method name in line 3, and the property key of the object source in line 14 is the same as func in line 3. This is similar to the example shown previously, but now the read and write are in different functions, meaning that they can't be syntactically detected. Second, the value in the correlated read-write pair is used as free variable. And third, the code uses type predicates to ensure only functions go into the true branch at line 4. State partitioning can't handle any of these three patterns, while demand-driven value finding can handle the first two by using a separate backwards analysis. Similar for the three challenges is that they all require relational information between two different abstract values. We propose value partitioning as a technique for providing this relational information between different abstract values. In the next slides, I will show examples of how value partitioning works and how it handles the three challenges. In other words, how value partitioning precisely reasons about correlated read-write pairs, free variables, and type predicate functions. For showing how value partitioning handles correlated read-write pairs, we use the same example as earlier, where property names are copied from the object X to the object Y, and P is unknown. At the dynamic property read, we partition the value like state partitioning, but instead of partitioning the entire abstract state, we only partition the abstract value. By only partitioning the abstract value, value partitioning avoids any redundant computations and is therefore much cheaper than state partitioning. Therefore, value partitioning can be applied at all dynamic property reads and does not need to rely on a syntactic pre-analysis. We represent the different partitions by different colors. The blue partition represents all executions where the value of p at the last occurrence of this dynamic property read was true. Similarly, the green and orange partitions represent executions where p was bar and where p was a property not in X. The value can now also be read in each of the partitions, so t becomes a partition value, indicating that the value of t is f1 when p was a string foo at the read, t is f2 when p was bar at the read, and t is undef when p was neither foo or bar at the property read. Now at the dynamic property write, we can exploit the partitions. At the write, we know that the value f2 can't be written to the foo property, since we know that p only is foo when p was foo at the read, and we know that t only can be f2 when p was bar at the read, meaning that the two values represent different executions. Therefore, it suffices to only write the value in the blue partition of t to the property name in the blue partition of p, and similar for the green and orange partitions. Therefore, after the write, we have only written f1 to the foo property in y, f2 to the bar property, and undef to the unknown property. We have thereby avoided mixing the properties together, and we did it without introducing new analysis states or using a separate analysis. To illustrate how value partitioning handles free variables, we use a slightly extended example. This time we create another function g, which returns the value t and writes the function g to the P property of Y. We start with the same analysis state as previously and analyze the dynamic property read exactly as on the previous slide. The interesting thing about free variable partitioning is what happens when creating the closure for G, when G has a free variable that is partitioned. Since T is partitioned in the blue, green, and orange partition, we also create the closure G in 3 different partitions, so the value of R is also a partition value with the same 3 partitions. Furthermore, we also annotate the closure itself by which partition it was created in, which is indicated by the coloring of G in each of the partitions. Notice the blue color for G in the blue partition, the green color in the green partition, and the orange color in the orange partition. This annotation denotes which traces the closure was created in, represented by the partition. The blue closure G therefore represents that the closure was created in traces, represented by the blue partition, meaning the traces where P at the last occurrence of the read had the value foo. We can exploit this information later when the function is called, since it suffices to only read the partition of T in which the closure was created. At the dynamic property right, we exploit the partitions, so only the blue G is written to the foo property of Y, the green G is only written to the bar property of Y, and the orange G is only written to the unknown property. Now, when calling y.foo, we are calling the blue G closure, meaning the closure created in the trace represented by the blue partition, and therefore it suffices to read the blue partition of T, which results in the value f1. We are thereby avoiding mixing the properties of X together, even though the value was used as a free variable in a closure. The last challenge is type predicates. The example program on the right contains a type predicate function isObj, which returns true if the argument X is an object and false otherwise. The isObj function is called, and depending on the result of the call, either the true or false range of a conditional is visited. Let's consider an analysis state where the value of X is either the string foo or an object with no properties. When we perform the call to isObj, the value of X is partitioned into a partition for each of its possible types. Specifically, this means that we have a blue partition representing the execution traces where X was a string at the call, and a green partition representing the traces where X was an object. We apply this type partitioning for all calls with a single argument, where the argument might be values of multiple types. The result of calling isObj is then also a partition value, where the value is false in the blue partition and true in the green partition. This means that when analyzing the conditional, the analysis knows that X only can be an empty object in the true range and only the string foo in the false range. We have implemented value partitioning in our tool TIES-valpar, which is implemented on top of the TIES static analyzer for JavaScript. The extension was in total less than 1,500 lines of code, which mostly consisted of boilerplate code for lifting some operations from the original abstract value to the new partition value. TIES is a state-of-the-art analyzer for JavaScript, which is implemented in Java and has been developed at Aarhus University for the past decade. Furthermore, all the results of TIES-valpar have been thoroughly soundness tested to provide confidence in the soundness of our implementation. We have evaluated TIES-valpar on 6 benchmark groups that consists of libraries, and each benchmark is a small program that uses that specific library. The first column lists which libraries we use, and the second column shows the number of benchmarks for that library. We compare our results to 3 other analyzers: TIES, which is the analysis we have extended, CompApps, which is the technique using state partitioning, and TIES-VR, which is the analysis that extends TIES with demand-driven value refinement. The results should be read as the number of benchmarks successfully analyzed, and in parentheses is the average analysis time for the successful benchmarks. For example, TIES-valpar succeeded analysis for 173 underscore benchmarks with an average analysis time of 2.7 seconds. The analysis for a benchmark is successful if the analysis terminates within 300 seconds with a sound result. As we can see, neither TIES or CompApps performs well on these benchmarks, so I will focus the comparison between TIES-VR and TIES-valpar. The results of the two analyses has some similarities, but Zeiss-Valpar also outperforms Zeiss-VR in some cases. Zeiss-Valpar can analyze all the benchmarks that Zeiss-VR can, and for the Lodash benchmarks, Zeiss-Valpar can actually also analyze 24 more cases, which is more than half of the cases that Zeiss-VR fails. Furthermore, we see significant improvements in analysis time for the prototype and scriptaculous benchmarks, where Zeiss-Valpar is 3 to 4 times faster than Zeiss-VR. To conclude, we have presented the new technique value partitioning, that is a technique for simple and efficient relational analysis. We have shown that value partitioning can precisely handle the challenges regarding correlated read-write pairs, free variables, and type predicates. Our evaluation shows that Zeiss-Valpar increases precision significantly with little overhead. If you are interested, you can check out our tool. It is open source on the URL provided on the slide. Thank you for listening.